Let's go over some necessary things you need to know about exponential functions and logarithmic functions that you need for calculus. Now, for exponentials, it's really just reducing and combining exponential expressions. There's not a lot of solving exponential equations. It could be used, but for the most part, as long as you know these properties that I've listed here, which are generally all algebraic properties, that's the most important thing. You will need to be able to, on occasion, use your calculator with exponential expressions, but I'm sure that most of you can handle that, as it is just a matter of typing into the calculator and then knowing that we have an exponent to use. Let me use my other one if that's going to be problematic. So for instance, if you needed to do 2 raised to the third power, that would be the expectation, that you would know how to do those sorts of things on your calculator, and I think most people are aware. If you need the value e, which is about 2.718, your calculator generally has a constant value of e in there already. And, if you need to raise e to the second power or something, it's taking 2.71828 is all the decimals I know, raised to the second power, which is going to be a little bit different than what I have because the calculator has more decimal places than I'm using. So, but that's the idea. All right, so algebraic properties. Something raised to the 0th power is equal to 1. A great thing that is needed to know for a lot of reduction. All right. Something raised to the 1st power is just itself. Something with a negative exponent, it's not a negative number. It just means to take that exponential part and move it into the denominator. Or if that negative exponent happens to exist in the denominator to begin with, you move it up to the numerator. The product of 2 exponential functions who have the same base can be combined into a single exponential expression with that same base. Or you can actually split it that way as well. A lot of times with reducing, splitting is the more important one. If you have 2 exponential expressions, and that's a typo, that should have been of the same base, but a different exponent, so a to the x over a to the y, would have combined into a to the x minus y. So you need the same base, but not necessarily the same exponent. And then to divide those, you just subtract their exponents. Some of the ones that students often forget, what happens when you have an exponential expression raised to another exponent? You can just multiply those exponents. And then likewise, it goes the other direction. So if you have something like, 2 to the 15th power, okay? You can, and you don't remember what 2 to the 15th power is. You could split it up. You could say this is actually 2 to the 3rd power and then to the 5th power. All right, so then 2 to the 3rd would be 8, and then you would be doing 8 to the 5th power. And of course, you would have to know what 8 to the 5th power is, but regardless, you can split these. You can go the other direction as well. That's the idea. All right, then a times b. Wow, there's a lot of typos here. A times b raised to the x power. So you have a product raised to a power. You can break that up into 2 different exponential expressions, each with the same exponent. The same thing is true with quotients. And then the last one here that I've listed is really for solving exponential equations, and there's really not a lot of that in calculus, so I'm not really going to cover that. What I want to do with you is I want to go over some example problems that involve reducing. That's usually what we're doing. So the key thing in reducing exponential expressions, just make sure you just take care of the negative exponents first. All right, so for instance, you have a negative exponent here, a negative exponent here, and a negative exponent there. Just make those all positive exponents before you do anything. All right, it's tempting to try and do like 8 steps all in one. But if you want to make sure you get the right answers, just take one thing at a time. So a to the negative 6 in the denominator comes up as positive 6 in the numerator, and then this b to the negative second in the denominator is positive b squared in the numerator. And then a to the 6 stays, b to the negative 1 goes down. All right, then I have this negative 3 on the outside. It is also negative. We'll handle that in a moment. All right, so for now, I can combine a few things. So I can say, for instance, b goes into b squared, leaving just a b. And then a to the 6 times a to the 6th would be a to the 12th over 3, and then to the negative third. All right, because this is a negative, it just basically inverts everything. So everything has a negative exponent. It's all in the wrong place. Everything just flips. So this is really 3 over 2a to the 12th squared. And then if you have an exponent outside a quotient, you just raise the numerator and denominator each to that exponent. So this effectively means I would have 3 squared over 2 squared times a to the 12th squared, which would be 9 over 4a to the 24th. So that uses kind of all those different properties in some way, but it reduces it to where it's a lot easier to manage than what we had originally start with. All right, so it's not like you're going to have a lot of these kinds of problems like on a regular basis, but you'll have little bits in between every now and then, which it would be useful for you to be able to reduce them when those come across. All right, so let's see. I could start off with negative exponent. So z to the 4th over x cubed takes care of that one. And then this would be 2x squared y z to the negative second. All right, now because that's to the negative second, that means everything in that set of parentheses gets inverted. So this is really 1 over 2x squared y z. That's a terrible z. Try again. But everything in those parentheses will also be squared. So I'm going to square all of that. And I'll handle this thing outside in a moment once this exponent's taken care of. So this would be 1 over 2 squared, x to the x squared squared again would be x to the 4th, and then y squared z squared. Now I'm going to start combining with the fraction in the front. Z squared goes in z to the 4th, leaving you z squared. X to the 4th, x to the 3rd would give you x to the 7th. So it looks like I would have z squared in the numerator. And then that's 2 squared, which is 4. Y squared and x to the 7th. And that looks like as simple as I can make it. Another quick example here. Let's see, I'm going to invert. So I'm going to make this, let's say, negative 1 over 2x squared. All right, the negative doesn't really matter if it's in the numerator or denominator, but you probably hate me if I don't, so I'll just put it there. And that would make this a positive 3, so I've inverted everything. The second one, I'm going to make 3y to the 4th over x squared to the 3rd. Now everything in parentheses gets raised to the 3rd here, so I could make this like 1 over negative 2 to the 3rd, x squared to the 3rd would be x to the 6th. 3 to the 3rd is 27, y to the 12th over x to the 6th. And then just combining like terms here. So I've got a negative because negative 2 to the 3rd is negative 8. So 27 y to the 12th over 8 x to the 12th. And there we go. So you just need to be comfortable with working with, reducing or combining exponentials. It generally wouldn't be as difficult as those examples there, but like I said, you can run into any of those rules at any time, and you just want to make sure you're comfortable with each of them. All right, logarithmic expressions. Again, just like with exponentials, there's not really a whole bunch to need to be able to work with here when it comes to logarithms. It's really reducing, expanding, and combining. All right, so the base idea of logarithms, some basic vocabulary. When you see the expression like y equals log base b of x, all right, y is called the logarithm itself, b is called the base of the logarithm, and x is the argument of the logarithm. So that's the terminology that we use here. The logarithm of any base of 1 is just equal to 0. Good thing to know for reducing stuff. A logarithm of base b of b is equal to 1. Now, why is that the case? Well, if you'll notice here, a logarithm is always equivalent to a similar exponential expression. So for instance, log base b of x is equivalent to the base raised to this value right here, y, equaling the argument. So it's kind of a mapping. It tells you how you can go from the logarithmic expression form to the equivalent exponential expression form. So this is the log form of this equation. So this would be base b raised to this value equals the argument. So this is the same statement as anything to the 0th power is just equal to 1. So that's all it means, all right? And the next one is a similar thing. b, which is the base, raised to this value is equal to the argument. So b to the first power is just itself. That's the logarithmic equivalent of that exponential principle. All right, now I'm not going to prove all of these, I'm just going to go through them quickly. The next couple are generally considered to be inverse rules. So if you do a logarithm of a exponential expression, it just cancels out, and you're just left with whatever the exponent is. Similarly, if you take an exponential expression, raise it to a logarithm of the same base, it cancels out, and you're just left with whatever the argument of the logarithm is. Now, the ones you'll use most are going to be 5, 6, and 7. So a logarithm of one base added to another logarithm of the same base can be combined into a single logarithm of the same base where the arguments are multiplied. This is the equivalent rule to what we saw up here in number 5 for exponential functions. It's just the logarithmic form of that rule. All right, and for 6, that's when two things are divided. It's just, the same rule as exponential expressions, but it's the logarithmic form. And then one that is kind of unique to logarithms is this, the logarithm of base b of x to the rth power. So if your argument has an exponent, you can bring that out as a constant multiplier. Now, when we use logarithms in calculus, it's often to simplify a process that we're about to do. And these 3 rules together, 5, 6, and 7, are often the rules that we use the most. And you want to be able to kind of use them to combine logarithms into a single expression or expand them out. One of those 2 types of practices is generally what's most used in a calculus course. So for instance, 1/2 logarithm, well, ln, for instance, is the natural logarithm. So 1/2 natural log of a plus natural log of b minus natural log of c. If I want to combine that into one logarithm, then any constant multipliers I can bring as an exponent on my logarithm. Okay, I usually tend to use a cursive L for natural log in writing. Now, a to the 1/2 power, that's the same thing as the square root of a. So this can be combined into a single logarithm, but it's going to be b times c square root of a. Because b times c, since they're, oh, sorry, my bad, that's those are subtracted. So that's going to change things. All right, so b minus c, that's going to put c in the denominator. So it's going to be b square root of a all over c. All right, so that right there, the 2 logarithms involving a and b are added, so we multiply those, and then we divide by c because it's being subtracted. All right, so that combines it into a single logarithm. Similarly here in b, I have log base 5, so this would be log base 5 of x cubed minus log base 5 of, I'm going to go ahead and change this into a square root of y, plus log base 5 of z. Now the x cubed and the square root of y, those are subtracted, so we divide those. So it's going to be log base 5 x cubed over square root of y. And then the z is added, so we would multiply, so put that in the numerator. All right, going the other direction is the exact same skill set. It just simply is going to be using the rules in reverse. So first off, I can split this up into two logarithms that are subtracted because of this division bar right here. So log of the numerator minus log of the denominator. Now, there's no base written in here, so this is called a common logarithm, and it's just assumed to be base 10, if you see that. All right, now the first two logarithms, I have two things that are multiplied together. I'm sorry, in the first logarithm, I have two things that are multiplied, so I can split that up into two logarithms that are added. And then finally, the exponents on the arguments of the logarithms can come out as constant multipliers. And if there's no argument on the, if there's no exponent on the argument, I tend to not use the parentheses. I try to only use the parentheses like if it's really necessary. Like if there's two things that are added, it's supposed to be inside the logarithm. You should put parentheses so it's very clear what's inside the logarithm and what's outside. But if it's just a single term, it's fine to not use parentheses and save you some writing there. All right, this next one is a natural logarithm, and I have a square root. So I can start off by writing that as a cubed b to the 1/2 power. All right, so that 1/2 power is an argument on the, is an exponent on the argument, and it can come out as a constant multiplier. Now I have two pieces inside the argument that are multiplied, so I can split that up into two separate logarithms. Now I do have to be careful because this 1/2 is still going to apply to both logarithms. So I'm going to put this in a second set of parentheses. All right, now I have an argument on the first logarithm. Sorry, I keep saying that. I have an exponent on the argument of the first logarithm. That can come out as a constant multiplier. And then for simplicity, I'm going to go ahead and distribute the 1/2 and say this is going to be 3/2 natural log of A plus 1/2 natural log B. All right, so those are the kinds of skills you need to be able to do. In addition, you need to be able to use your calculator for logarithms, so let's go over that real quick. Now, as I've already mentioned, you have two main types of logarithms. Those are the ones with names. You have a common logarithm and you have a natural logarithm. Common logarithms are denoted log x, and that's a base 10 logarithm. Natural logarithms are ln x, and that's a base e logarithm, where e is that number that I mentioned earlier, 2.718 and so forth. All right, now, these are the only two that most calculators will work with. And sometimes it gets a little bit more confusing than that because, like the TI, for instance, when it says log, it means a common logarithm. And when it says ln, it means a natural logarithm, so base e. Other calculators will use log as the natural logarithm. So log will mean log base e, and then there won't be a natural logarithm. So you have to just kind of look up for your particular calculator which one's which. But I tend to teach with the 84 whenever necessary, so I tend to just use the notation used there. So now, those are the only two bases that most calculators can do. And some, like I said, can only do one. But that's okay because you can actually change the base of a logarithm pretty easily using the change of base formula. And I've written out the full form here, but the way I use it is basically this. Log of any base of x is the natural log of x divided by the natural log of the original base. So to use your calculator, you're going to need to know that rule. Now, if you need to do a natural logarithm of a number, that's probably the most common thing in a calculus course. Then you just use the ln function, type in ln5, get the approximate solution here, so 1.609, and I'm going to use the approximate symbol here, so 1.609. If you need a log of 3, so that would be a common logarithm of the value 3, 0.477. That's fine. So this is approximately 0.477. Now, log base 2 of 5. To do this, you have to use the change of base formula. So you have to take the natural log of the value, so of the argument, divided by the natural log of the original base. And that effectively changes the base to base e, which your calculator can do. So natural log of 5 divided by natural log of 2. Just make sure you close those parentheses, otherwise you're putting the denominator inside the first logarithm and it gives you the wrong answer. All right, so 2.323. So I should say that's approximately 2.323. And that's how you use your calculator with logarithms.